Welcome to lecture number 6. And you may recall that in lecture number 5, we ended at a certain point in our calculation of energy in magnetic field. We arrived at one version already. Energy is denoted by W. Okay, is equal to for a circuit with self-induct. Let's see. Right, it's given here, that's right. It's given half L, okay, half times the self-inductance times I squared. So it's proportional to I squared. And then we rewrote those in terms of something even more useful, so that we wrote down W as volume integral of J dot A. A is the vector potential, J is the volume current density, and we're supposed to do the volume integration over a volume, at least including the region where J is non-zero. Of course, you can include integration over a larger volume, but this extra volume would contribute nothing to this, since J would be zero there. But so long as still in the volume integration, you include the region where J being non-zero. That's good enough. All right? And then we make use of the Maxwell's equation in particular. The last one. The Ampere Maxwell equation for this, and for our case, for what we're talking about here. This term's not there. There's no del E by del T. So that we are left with, so J would be just given by the curve B. And then, so that this expression is nothing but the volume equation of A dot curve B. And then I noticed that, in fact, this can be written as the difference of two terms, namely that is the difference of this term and that term. So that this, what we're interested in, can be written as B squared minus divergence of A cross B. A is the vector potential, B is the maximum, obviously, magnetic field. So I've copied down here. So that there are two terms, B squared, and then this divergence of A cross B. And we're supposed to do the volume integrations over a region at least as large, well, including the region where J is non-zero. All right? Since I can do the volume integration for a larger volume, so in fact, let's go to the volume including all space. Okay. We don't have to do anything about the first term. The second term, let's see what happens. The second term has to do with volume integral of divergence. Okay, of course, by making use of Gauss theorem, we can replace this by area integration of A cross B. So if we now do the integration over all space, then this second term also involves volume integration over all space. That means that the surface integration would be on the sphere with radius r tending to infinity, large R. Let's see what it looks like to that area integration for this A cross B. Of course, we can expand the vector potential and the magnetic field in make a multiple expansion. And the lowest type of multiple is the dipole. And we know that the dipole moment, vector potential, falls off with distance, like 1 over r squared. And B, for the dipole moment, falls off like 1 over r cubed. So that this product will fall off at least as fast as 1 over r to the 5th power. But the area okay, goes up only as r squared. So that for large r, okay, this goes away. So that okay, W is equal to 1/2 of the mu naught of the volume integration over p squared over all space. So this is another useful form for the energy in magnetic field. Well, this form of the energy for the magnetic field should not come as a surprise at all, because after all, we have found out that the energy density for an electric field E goes as this, and for the magnetic field B goes as the energy density goes as 1/2 over mu naught B squared. So if we integrate over all space, then of course that will give you the total energy. So this is result we have derived is consistent with what we have with what we derived in the last lecture. Not only that, you remember that we had another form of W, namely this. Only half of volume integration of J dot A. And let me remind you at this point that, in fact, from chapter 2, I think, of Griffiths, which you went over last semester, for the electrostatic case, the energy is 1/2 of d tau v rho, which is of the same form as for the magnetic case. And also, when it also can be written in this one, which is the counterpart of this result, which of course is also not surprising, since this is consistent with the energy density for electric field E is given by this. So that the total energy is given by this half epsilon naught E squared integrated all space. So everything is consistent. So this concludes, I think, chapter 7. And we have done part of chapter 10 and chapter 8 already. Okay, the next thing that we are going to cover will be, and I may have used for some of these results, so let me leave them here, and let me erase all this. Let's start our discussion on electromagnetic waves. It's a very interesting topic, as you will see. Let us start the discussion with Maxwell's equations in vacuum with no sources. So let's start with Maxwell's equation with rho and J being 0. So that we have, curl of E is 0, so is curl of B. And, oh, I'm sorry. Wow, I didn't even realize that I wrote something completely nonsense. No, this is divergence. Oh boy. I didn't even notice that. Divergence. My own excuse is that it's very hard to talk, think, and write at the same time. All right, and this, the curl of E okay, is so in vacuum, and with rho is 0 is J 0. Okay, minus del B by del T. And the last one, okay, being curve B is equal to this term is epsilon. I have epsilon naught mu naught del E by del T. Obviously, all of those four equations are first order differential equations, but they are coupled equations. E and B are coupled. And to solve the equations, which is advantageous to decouple the equations. How can we do that? One way to do that is the following. Let's take a look at the curve E and take the curve of this equation. So I'm interested in curve of E. That will be equal to minus del by del T curve of B. Okay? And the left-hand side involves triple cross product, so that there are two terms equal to, one term is in the direction of gradient, and like that on both this gradient x on the E, so gradient times gradient dot E. That's the first term. And second term is in the direction of E, is multiplied by this dot that, which is the Laplacian. That's the left-hand side. Then the right-hand side is equal to, well, curve B is given by this. So that you have del by del T, del by del T, so del by del T squared. And there's a minus sign, minus epsilon naught, mu naught, del squared by del T squared E. Now it is a second order differential equation involving only E. So we have decoupled E and B. And we can simplify this because of the fact that the first equation says divergence of E is 0. That is 0. So that we have, can join the minus sign, the differential equation, Laplacian acting on E, which depends upon location R and time T, is equal to epsilon naught mu naught del squared by del T squared E as a function of R and T. Second order differential equation. And you may notice that I can put this term to the other side so that I have the combination of Laplacian minus epsilon naught mu naught del squared by del T squared. And you remember that those two terms combined in that form to be the D'Alembertian. But let's give it in this form. All right? We use this equation to the curve, we got this result. Of course, we can start with this equation, take the curve, and then do the same thing. We'll get an equation for B instead for E. Actually, we don't have to do that. All we have to do is to use this equation and make a duality transformation. And it's easy to convince us that, in fact, B also obey the same differential equation. B B as a function of R and T. Continue here. So both E and B obeyed this kind of differential equation, so that it is they are of the form del squared f certain function of R and T is equal to 1 over v squared del square by del t square f of rt. They are both of this form, the differential equation. Here we have put, okay, v square, which is square speed, okay, del t square, so that we will match the dimension. This is Laplacian square has dimension 1 over, okay, length. So that now this is 1 over square of, okay, speed times t is length square. That's correct. And we know that this is the famous, okay, wave equation, classic form. Wave equation. Propagating with speed v. And let's in fact talk about the one-dimensional case, so as to establish, okay, in a simple manner, okay, the terminologies. So let's say instead of 3 dimensions, let's just talk about 1 dimension, the x dimension. So del square by del x square f of xt is equal to 1 over v square del t square f of xt for 1 dimension. This equation is, as we said, famous wave equation, and the solution is well known. Namely, the function, okay, would be of the form with the argument depending on x and t being, okay, like this: x minus or plus vt. This is solution. Okay, the dependence on x and t come in this form, okay, combination. And okay, plus or minus here, okay, depends upon whether the wave is propagating towards plus x or minus x. So this corresponds to, okay, a wave of constant shape propagating, okay, along x. Okay, and okay, let's, okay, so that a particular point on the wave will correspond to a certain fixed argument of the function. Okay, so let's consider, okay, a certain fixed, okay, with a value for the argument, x minus or plus vt equals constant, certain constant. And we can now, okay, take a derivative with respect to time for this equation. So that you have dx by dt minus plus, okay, v is 0. So the dx by dt is plus or minus v. So that, okay, we identify, okay, the x minus vt condition as the right moving wave. Namely, the wave, okay, moves towards positive x direction. And, okay, the x plus vt, okay, for the argument of the wave function, correspond to a wave propagated in negative x direction. And not surprisingly, the speed is v. All right. And, okay, next, okay. So that means that if we, okay, apply this result to our wave equation for the, okay, electromagnetic field, okay, we see that, okay, 1 over v squared is given by this. Okay, 1 over v squared is given by epsilon naught mu naught, which, okay, if you, okay, work out, okay, the numerical value for the product of epsilon naught mu naught, okay, it comes out to be very precisely, okay, 1 over c squared, with c being 3 times 10 to the 8 meters per second. So that even in vacuum, okay, you can have electromagnetic waves. So the vacuum support propagation of instrumental waves. And that the instrumental waves propagate with a speed equal to speed of light in vacuum. And that shows that light is indeed an electromagnetic wave. Fantastic result. Okay, so we have been talking about the vacuum case without sources. Now let's generalize the discussion to the waves inside matter. And let me see, I've erased it. Yeah, I thought I planned it very nicely. No? Huh. Oh, here! Inside matter with no free charge density, no free current density. Okay, the Maxwell's equations are given by these 4 equations involving the displacement vector, electric displacement vector D, and H vector, and the usual E and B field. And for linear media, D is related to E times the permittivity of the medium, and H is related to the B field by multiplying by 1 over the permeability of the medium. Now let's talk about matter such that there's no free charges, no free current, and that we are talking about a homogeneous linear medium. For a homogeneous linear medium. By homogeneous, I mean that permittivity and permeability being constants independent of location. All right? In that case, D is nothing but this constant times E. Constant will not be acted on by the derivative, so that it becomes the usual. Oh, gosh, I see. I made a mistake here. Dot. Oh, sorry. I was just copying down the wrong thing up there. Okay, so dot, epsilon E, epsilon can be put outside, since that's 0 on the right hand side, so it becomes divergence E is 0. But this equation remains the same, divergence B means 0. And this equation remains the same. Curl E is given by minus del B by del T. And how about this equation? This equation, H is 1 over mu B. 1 over mu B can go to the other side. And then D is epsilon E. So that you can rewrite this as curl of B is equal to this, because as a mu, so epsilon mu del E, I'm sorry, del E ray by del E by del T. Now let's take a look at these 4 equations as compared to the 4 equations in vacuum without the sources, which is here. And you see that this equation, same as that one, this equation, same as that one, this equation, same as that one. The only difference is in the last equation, with epsilon naught mu naught for the vacuum case, replaced by epsilon mu. So that, right away, read, know that the speed of propagation is base 1 over v squared is equal to, instead of epsilon naught mu naught, is epsilon mu. All right? So the V is equal to square root of epsilon mu. And V very often is written in terms of C, the speed of propagation in vacuum, as C divided by N. N is the index of refraction. Or, we can write this, or, since C is nothing but, C is nothing but, the reciprocal of square root of mu naught, epsilon naught mu naught. So the V can be written, N can be written as square root of, N can be, oh, I'm sorry. This is inverse. No wonder. Okay. V is inverse square root of epsilon mu. Sorry. So the N is given by, since C is given there, C is equal to 1 over square root of epsilon naught mu naught. Is that right? C squared, yes. Okay, the reciprocal, right? That. So that I can write N as square root of epsilon mu, divided by epsilon naught mu naught. For all the transparent materials that I know of, the permeability is very close to the permeability of vacuum. So that this mu over mu naught is roughly 1. And for all the transparent materials that I know of, the permittivity is greater than the one in vacuum. So that we expect the index of refraction to be greater than 1. And that is as observed in nature. All right? We'll come back to talk about propagation of waves inside matter later on. But let's continue to talk about electromagnetic waves in vacuum. And we are now ready, in fact, to introduce some of the definitions, some terms. And where should I do that? Yes. Let me keep this one. We are done with this, since we are not going to talk about propagation inside matter in this lecture. Let's go back to the wave equation here in one dimension. All right? And so that we'll have F. Let me talk about the case for propagation towards the positive x direction. So it's x plus vt. The wave that's most familiar is the sinusoidal wave. And for very good reason, because all functions from your study of Fourier analysis can be written as linear combinations of sinusoidal waves. So let me write this as a sinusoidal wave solution. So this is, let me write this as sinusoidal wave function. It's equal to A cosine, k times x plus vt. This is the most familiar form of the wave equation. All right? In general, in fact, there could be a constant inside phase inside a cosine plus the delta. This delta as a constant is known as phase constant. A is the amplitude. And k is known as the wave number. Wave number. Let's consider this wave at a fixed time. So this is constant, this is constant. So let's imagine that we advance x by a certain amount, so as to make k times the change of the amount to be 2 pi. So that k x advanced by an amount which I will call lambda is 2 pi. In that case, when x is advanced by this length lambda, the argument of cosine increases by 2 pi, so that the cosine function goes through one cycle. This length lambda, by which x advances or goes backwards, is known as the wave length. Is equal to 2 pi divided by the wave number. Next, let's consider the wave function at a fixed location. So this x is fixed. So we are talking about the wave function at a fixed point, a fixed location. And the wave would is depends on time as cosine something kvt. So that wave oscillates at that point, up and down, things like this. And as time goes by a certain amount, the wave repeats, goes through one cycle. So let me see. So let's say that kv times a certain amount of time, that is equal to pi. And t in that case equal to pi divided by kv. The amount of time that that wave the wave would change by 2 pi, will go through one complete cycle up and down, is known as the period of oscillation. It's written, denoted by t here. And what's that? That can be written as, since 2 pi over k is nothing but lambda, 2 pi over k, 2 over k. So t is lambda divided by v, if I'm not mistaken. Right. K lambda 2 pi, right. kv t is 2 pi, so t is 2 pi to kv, kv is 2 pi over k here, so it's lambda, right, correct. That's t is known as the period of oscillation. Now, the reciprocal of the period, 1 over t, gives you the number of oscillations per unit time. Okay. And this denoted by nu. So this is the frequency of oscillation. And nu is equal to 1 over t, so that is v over lambda. Quite often, people, instead of using the nu frequency, they use the angular frequency. More than not, people use angular frequency, which is denoted by omega. Omega is nothing but 2 pi times the frequency nu. I hope you can tell the difference between my nu, which is frequency, and v, which is speed of propagation. So what's that? 2 pi nu, so it's 2 pi, let's see, So it's V, the 2 pi over lambda. But 2 pi over lambda is nothing but k. So that the angular frequency, omega, is related to the wave number k by Vk. In that case, we can go back to the original expression for the wave function. This is kx times kv times t. So kv is nothing but omega. Oh, I'm sorry. I'm so sorry. Okay. Well, in my notes, at least, it doesn't matter in a way. Okay. We want to talk about the right move in the wave. So it's minus. Okay, now I can write the argument as kx minus kv. Kv is omega t plus delta. Continue. And I still a little bit space here, but not enough. And back here is this. Oh, yeah, we are working here. So I think we can erase all this now. We do not need any. Maybe we can keep this here. Okay. Erase this. All right. What's next? And we have found, where is it? Oh, it's behind it. So that, we're talking about a sinusoidal wave. Okay, which is now, let me copy it. Oh, well, we are done with all this actually. So that in fact, we can erase all this. Let me keep this here. Now, as you may recall, the famous Euler formula, namely that exponential e of I, say, what do we call it? Delta or eta. That can be written as the real part being cosine eta, the imaginary part being sine eta. Hence, this function, wave function, can be written as a exponential of I k x minus, now Vk is omega minus omega t, oh, it's here, minus omega t plus delta. All right? And the cosine part is the real part of this. We want to do that, use this form, because it is easier to deal with exponential functions rather than the trigonometric functions. And we can also, in fact, A is the real amplitude, it's a real number. And we can combine A with this factor coming from the phase constant, e to the I delta. This now would be a complex number, and we use the twiddle to represent complexified amplitude. So this is the definition of A tilde. So this is the real part of A to the e to the I k x minus omega t. So that is a sort of function that we would be interested in would be of this form. Okay, we do all the necessary calculations using this form, and then take the real part eventually to find the solutions for the wave function. There's A triple, sometimes it's known as complex amplitude. All right. So now have I done all the necessary preliminary work? Let me take a look at my notes so as not to miss anything important. Are we ready? Yes, that's what I thought. We are now ready to talk about electromagnetic waves in vacuum. And then I use this. So, electromagnetic wave, wave in vacuum without sources. Okay, so that we know that our electric field E and magnetic field B can be written as in terms of this kind of wave. So let's talk about plane wave. Propagating in the x direction. Propagating in positive x direction. And let's talk about the x positive direction. Then, of course, I can write my E, which is a function of R and T, as following as amplitude E naught times cos. Do I want to introduce that at this point? Okay. Yeah, may as well. Let's in fact go right away to the complexified wave. So the complexified amplitude times E propagating in the x direction, so E to the I k x minus omega t. Of course, we're interested in the real electric field E, then we just take this and take the real part of it. So that the complex amplitude for the electric field E is E naught. This is a vector, this is a vector. Amplitudinal means complex, it's a complex amplitude. And similarly, the B field is the amplitude plus E to I k omega minus omega t. When we talk about plane wave, that means that there's no space space dependence in the amplitude. So these are constants, independent of x, y, z. That's a plane wave. All right, and with that, we can start our discussion. First of all, we know that omega, omega and k are related by this. But now the speed of propagation v in vacuum is c. So this is c. So omega is related to k by c k. All right. I wonder. Let's see. Okay. Continue here. Now let's go back to the original Maxwell's equations for case of vacuum with no currents, no charge density, this, and complexify these equations. I can do that. Okay. In that case, we are told that divergence of E to do is 0. Let's take a look. E naught amplitude is a fixed vector, fixed constant. The only spatial dependence appears in the exponent, this. So that, there's, of course, got 3 terms. The only term that can potentially be there is the one being del by del x. E x. The x component of this E field. The other 2 terms involving del by del y and del by del e being 0 because of the fact that there's no y and z dependence in the wave. What is del by del x acting on the x component of this? X component of this, of course, involves the amplitude. The x component of that amplitude, e to the I k x minus omega t. So that d by del by del x, now x on, this is a constant, x on kx, to bring down I kx. So that we have I k times e not the x component is 0. K is not 0, otherwise there will be no propagation. So that we have come to the conclusion that the x component of the wave is 0. That means that, remember x is the direction of propagation. And the amplitude along the direction is 0. That means that the wave is transverse. Oh, I should have mentioned that. Similarly, the argument works for the B, since divergence B is 0. So that we also learned that the x component of the magnetic field B is 0. That means that the wave is transverse. So that if the wave propagates towards the x, then the wave got to be transverse to this. So that there will be only y and z components to the waves, to the electric waves, and especially to the magnetic waves. Next, I wonder if I think we can erase this now. We know the result, but I will keep this here. All right, now let's take a look at this equation. We can do this equation also, but in fact, there's no need to do that because these 2 equations are related by duality transformation. We only have to do one of them. So let me take this equation and look at, the y component of this equation. All right, y component, the right side would be minus the b component, the y component of b by del t. And the left hand side is the curve. So that let me draw x, y, z. So the first term, the y component is del by del z x on E, the x component, minus, the other way around, del by del x, the z component of E. The x component of z of the electric field E is 0. We just find the first term is not there. Okay, this B field. Okay, let me. Yes, here. Okay. Derivative with respect to time will bring down a factor of minus I omega. So this is minus is plus. I hope I minus correct. I omega. Right? I omega. Times by. And this derivative with respect to x of E will bring down factor of ik. That's my side. Oh, both my side minus. That's my side, then ik times the z component of the electric field E, which of course contains the exponential function, both of them. So that what's left is, in fact, these two functions on the two sides can cancel. They're the same. So that I'm left with this. And you can do the z component calculation for this equation. But actually, you do not do it. You can use this equation and use duality. Okay? E goes into B, B goes into minus E, aside from factors of the square root of epsilon naught mu naught. All right. So then what do we get? Okay, let me in fact cancel out the I first. So that this equation will go into, let's see, omega y goes into z goes into minus z, minus plus k e not y. Okay, and check it. Okay, that's what you get. Okay, so that you can see that in fact B is related to E as k over omega times E times E well, cos, I hat, cos that. I hat, is unit vector along the x direction. It's the direction of propagation. Let me check. Okay, so that k over y is taken care of. Okay, that's y. Okay, this y would be k over omega, and then there's this. The y component is, let me draw this. So let's say that, this is I direction, x direction. Let's say that this is y, Remember, E and B do not have any x component. It's transverse wave. So let's take E to be along this direction, then B got to be along this direction. Because, B and K, B is also orthogonal to the direction of propagation, and it's also perpendicular to K as found by this. So let me check. So let me see if that's correct. The Z, Y component, let me take this to be X, Y, Z. So let me, for instance, take this to the Y direction, this to be the Z direction. So take this to be the I direction, so this is X direction. and then I cross E would be Y. Okay, so is that correct? So that is consistent with this picture. And let's see, Y is that times EZ, correct? Okay, and here Y has no doubt, correct? Yes, and YZ is that, all right. So that in fact, for the wave propagating along the positive x direction, B and E are related by this. And we can also simplify this fraction k over omega. K over omega is 1 over c. That's to be expected, since B has the dimension of electric field divided by speed of light, divided by speed. And the only speed here is speed of light. Okay, so there's many small things that we have to go over. So let me see. I have, correct. What's next? All right. So B triple is the amplitude times this exponential function. Similarly, E is this amplitude times this same exponential function. And this exponential function cancels on both sides. So that we are left with, this will not change, the magnitude. So that we conclude that, the following is true, namely that, and all these are real, so that this complexified field, B field, and this complexified B field are related by something real, so that we know that the phase hidden here, remember, this complexified amplitude is the real amplitude times the phase factor. This. So that the two phases are the same, in order for this to hold. Therefore, this is true, namely that the amplitude, the real amplitude for the B field is related to the amplitude for the E field by just this factor, 1 over c. And there's so many small things that I want to go over. All right. And I will come to that in a moment. So, all right. Let me stop here and continue. Okay, so I was saying that the wave, instrumental wave, traveling in the vacuum is a transverse wave. So that the instrumental wave can only be non-zero in a plane perpendicular to x. In a plane, there are two independent directions. So there are two possible polarization states. And it's customary to talk about polarization vector as the direction of the E field. Let's do it here. Polarization vector. Let's call it n hat. This is the direction of E. E is something in this direction, n hat. And n hat, of course, line on this plane perpendicular to the x direction, so the n hat dot I hat, which is the unit vector along the x direction, is 0. So then now we can write down the n hat can only have the y and z component, so that it can be written as cosine of certain angle j unit vector along the y direction plus sine theta k hat, where k hat is along unit vector along z direction, and the electric field E is along this direction as far as the direction is concerned. This n. Okay. Let's now right away go to the real wave function form for the electric field E and B, and I can erase this now. I can total this. Let me keep this here. The amplitudes are related in this fashion. Erase. Wait. Okay. Yeah. Oh, by the way, say if you have a wave function, propagating, instrumental waves propagating not along the positive x direction, but along say an arbitrary say k direction. This propagation direction. Then you can write down the form for the waves, for example the electric waves, to be this E naught e to the I, instead of kx, now it's k dot r, where k is given by its magnitude times this unit vector along the k direction. And this k here, I'm afraid, I can use ek instead, so as not to confuse with the unit vector along the z direction. Let me use ek. So ek is okay. Minus omega t. And if it is has certain polarization state given by n, so that this is nothing but E naught, the magnitude of derivative, times n along the n hat, where n hat is perpendicular to this direction of propagation. And B is very simple. It's 1 over C, of this now is replaced by ek hat. Ek hat, direction of propagation, cross E, cross this n hat, and this being now this have taken care of 1 of C in the amplitude B naught, so the rest is just this. E to the I k dot r minus omega t. With, as I said, the polarization state n hat being perpendicular to the direction of motion, also perpendicular to the B field. The polarization vector is defined to be the direction of the electric field E. Okay, and let's see. Let me continue. Let me catch my breath. Let's go back to the propagation of waves along the x direction. And I can now use all this. Now erase this. So let me consider an instrumental wave propagating in vacuum along the x direction. Okay, and let me use the plane wave solution. Talk about plane wave solution. Okay, so that E of x and t traveling along the x direction is the amplitude. E naught. Go back to the sinusoidal form, sinusoidal waveform, cosine of kx minus omega t plus delta. See, let's say that in fact it is along the y direction. Direction of propagation just is along y direction. Let's take that. So this is J hat. And then the B wave would be have an amplitude related to E naught by this factor. 1 over C E naught cosine kx minus omega plus delta. It is perpendicular to direction of propagation and direction of E. E is along the y direction, J direction, so this must be along the K direction. Let's do that. Okay. So that the amplitude for the electric field E is this. The amplitude for B is given by that. Okay. Now let's take a look at this wave, and let's take a look at the energy density corresponding to these waves was given by this expression. I want to put it here, otherwise you cannot see. Take this. So that the energy density for this wave is given by 1/2 epsilon naught E square. E square is I can E square is E naught square, and then I have cosine square. Kx minus omega t plus delta. That is this term. And then this term is 1/2 plus 1 over mu naught times b square. B square is here. I have cosine square here already. So this one I have 1 over c square E naught square. This is term. This comes from the magnetic field B. This comes from electric field E contribution. But notice that 1 over c square is nothing but epsilon naught mu naught. So this mu naught cancel. So this is nothing but epsilon naught. Lo and behold, the electric field contributes that much to the energy density, but the magnetic field B contributes the same amount of energy density. They contribute equally. For the case of propagation of waves in vacuum, we will see that in general that's not true. For example, when we come to talk about propagation of waves in conductors, we will find out that the energy density of the wave is dominated by the contribution from B field rather than E field. But it's nice, for the vacuum case, they contribute equally. So that I can write this as this being same as this one. So okay, forget about this, okay, half factor, this. So it's that. Epsilon naught E naught square. This is, okay, the energy density of the tremendous waves propagated in vacuum without, okay, sources. Next, okay, let's work out, okay, the, okay, Poynting vector. Poynting vector, and I think there might be, okay, after this there might be all we'll have time to do, okay, and let me use this side, the blackboard. So now let me work out, okay, what is the Poynting vector? Poynting vector is, okay, 1 over mu naught E cross B. E is here, B is here. E is along the y direction, okay, B is along the k direction, so that, okay, this cross product is along the x direction. So it's equal to I hat 1 over mu naught. So the Poynting vector propagates in the same direction as the wave. Thank goodness. Got to be, because the wave carries, okay, energy. So that, okay, the flux goes, okay, flows in the same direction as the wave goes. There's a consistency check. Good. Okay, E cross B, the cross product is given here already, direction. So that I now have this times that, so it's given by 1 over C E naught square, then cosine square of that. Let me just use dot dot dot. And so what do we have now? Okay, so this. Okay, so this, let me see how this is related to U energy density. Cosine square is there, E naught square is there. Okay, so if I divide, so this is equal to I hat 1 over mu naught, okay, 1 over C, okay, and let me, okay, multiply by epsilon naught, and then divide by epsilon naught, then I have, okay, epsilon naught E naught square cosine square. This, of course, is nothing but, okay, the energy density of the wave, U, E, B. And I can simplify this. Let's see. I have here 1 over mu naught, 1 over epsilon naught, and then 1 over C. Mu naught, epsilon naught reciprocal is nothing but C squared. C squared divided by C is just C. Along, okay, the direction of propagation. That's to be expected. U is the energy density. S, the Poynting vector, is energy flux. So energy flows with speed v c in the direction of propagation. That's a good check. And of course, okay, we can also write down, okay, the what? Have I erased it? We can also work. Oh, here. Well planned. What about, okay, the momentum density? It's given here in terms of the, okay, Poynting vector. So that, okay, the momentum density is given by, okay, epsilon naught mu naught. Of course, it's nothing but the reciprocal of c squared times s. So this is equal to, one of the c's cancels, so 1 over c u e e times I. So this is the momentum density. Right, divided by, so momentum is energy divided by speed, correct. All right, now we have all the results that we need for the time being. Okay, so what's next that I should mention? Okay, is, and U is already done here. Wait a minute. Oh, U is here. Given here. All right, and we notice that all this, quantities, being quadratic in cosine square, and cosine square inside cosine square is this, kx minus omega t plus delta. Oh, it's easier, just write down instead of. Now this is the frequency. Now for visible light, the frequency is very large. Namely, I think one oscillation, the period of oscillation is something like 10 to the minus 15 seconds. Is that right? Let me check and make sure that I do not say anything stupid. Oh yes, period of oscillation is something like 10 to the minus 15 seconds. So for any microscopic measurements, since this oscillation time is so small, for any microscopic measurements, involving the electromagnetic waves, of light, that will involve a lot of the oscillations. So the one we're interested in would be the average value of those energy density and the Poynting vector, etc. And I will use bracket to stand for time average value. All right. So that the time average value of, let me just drop subscript EB. This is understood to be the energy density of the electromagnetic waves. That would be equal to, the average value of cosine square is 1/2. So that, epsilon naught E naught square 1/2. And, PS, of course, is average value is, this C times that. So 1/2 epsilon naught C times E naught square along the direction of propagation, and similar for P. Now, the Poynting vector has the meaning of energy flux. It talks about the energy flowing along the direction. So let's now in fact introduce the term intensity of the electromagnetic waves. Intensity is defined to be the average power per unit area that is propagated, that's transmitted along the direction of motion. So that this intensity, of course, is nothing but the magnitude of the Poynting vector, average Poynting vector. So this is equal to 1/2 epsilon naught C times the amplitude of the electric field E squared. And I think it's good place to stop. So next time, we will talk about propagation of electromagnetic waves through a linear medium instead of through a vacuum. So let's stop here.